Okay, let's see if I can keep this one short as well. This is video 5 for week 7, and this is more examples on graphing. Let's see what we can do here. All right, so this says sketch or graph, and in this case it doesn't tell you anything else. I'm just going to say sketch and use your judgment. Okay, so this actually is written in the way your high school teacher would write it, but I'm going to rewrite it, like I told you, in the way you should be thinking, which is you should be thinking about polynomial as being things multiplied together, terms like pieces multiplied together, factors rather than terms. So this is in term by term, and this is factor by factor. Think of it that way. Okay, so over here you have, it looks like x squared, which, I mean, there's, you see x squared sitting there. So it's going to look kind of like this here. And then there's a root at 1, but it's just a regular pass-through root. So I'm going to pass through like that. But there's a problem, right? Because it's going the wrong way, right? This guy is going off to negative infinity, and this guy is going off to positive infinity. That's not the way it's supposed to look. It's supposed to go the other way. So let's try flipping that guy around, and then all will be well. There we go. That's what we really wanted. Okay. Let me erase these guys, because they are not quite right. So if that's all it said, I couldn't fault you. That's a pretty good picture. So the zeros are at 0 and 1. The max is here. The local max is at 0, 0. And there's a local min somewhere down here. Let's find out where the local min is, just for fun. So y prime is 3x squared minus 2x, which if we factor out an x, we get 3x minus 2. So y prime is 0 when x is 0. We already knew that. But the other place is at 3x minus 2 equals 0. Put the 2 on the other side. X is equal to 2/3. So right about here. Excuse me. Let's see. What is the y value when x is equal to 2/3? Okay, you can work that out yourself if you want. This is going to end up being minus 4 over 27. And the point of inflection, because we have a cubic, we have, of course, a special deal on cubics, so the point of inflection has to be at 1/3. It has to be halfway between that max and that min. And also it tells us that this point of inflection, it has to be 1/3 minus 2/27. So that's a trick we know because it's a cubic. But you can actually just calculate that out using calculus and pretend you didn't know the trick. Second derivative is, we have to go back to this guy to take the derivative. 6x minus 2. And again, if this equals 0, truly enough, x is 1/2 is going to work there. Sorry, x is 1/3 is going to work. And then if you just find y of 1/3, you can work it out and find out that it actually is minus 2 over 27. So if you didn't know this special trick, this is how you'd figure it out. Okay? Okay, that's enough for that example. I'm going to give you a question from the book. This is, I think this is verbatim one of your homework questions. If not, it's very, very similar. Okay. For what values of A and B will this guy have a minimum at 2, 5? Okay? And the question itself actually seems to contain information. And the point is, they're essentially telling you that there's a family of functions that has these two different things you can tweak, these two parameters, A and B. A is going to change just the stretch of everything. So for example, if I had a function that looks like this and I multiply it by 2, it's going to look kind of like that, right? So that's what A can do. But what does B do? I don't know. B changes something about the curve. And so we can go through and figure out what is happening. What does A do? What does B do? We can just take derivatives and see what happens as well. But I want to show you what it looks like, okay? And I think in the book they actually gave you a plot, so you knew roughly what it looks like. So never mind the A for now. I want to just talk a little bit about this, and then we'll go on and do the calculus. Okay, this part of the graph is essentially just x, right? Because here, I want you to think about this. What does natural log look like? Natural log looks like that. Okay, so this part is fast. It just has this asymptote, and this part is slow. Natural log of x grows slower and slower and slower and slower. And so when you add it to x or subtract it from x like you're doing over here, once you get into this range, this zone, then x is going to be the thing that matters the most, okay? But in this range over here, I'm going to make this blue over here, x is really, really close to 0. Like if you just plot y equals x, in this zone here, x is not doing much relative to what this guy is doing. And this is a subtraction, so it flips it from down there, it flips up there, okay? So this little bit here is mostly the minus natural log of x piece. Okay, so that's just a rough idea. Those two regions of the curve, the blue part is mostly dominated by minus natural log of x, and the red part is mostly dominated by x. And what those two things are doing is they're fighting, okay? And so this b here, this b, is going to stretch that natural log of x arm over here. You see? And that's what it's doing. And so it's going to make some kind of adjustment. Whoops. It's going to essentially adjust what's going on down here. So we want to know how we can adjust A and B so that we can force this minimum point to occur at 2, 5. That's what we're trying to do. All right. So let's go ahead and take the derivative. A is a tag along. Then a derivative of x is 1. B is a tag along. Derivative of natural log is 1 over x. Okay, so f prime is equal to 0 when? Well, a is not equal to 0. A is not going to be able to be 0, so this piece must be what's actually going to 0. 1 minus b over x must be 0, or 1 is b over x, or x is equal to b. So what it's saying here is that x must equal b at this minimum point. Well, that's kind of cool, because we got that kind of for free. We didn't have to do that much work to find it. So now we can plug 2 back into this formula, and let's see what's going on. So I'm going to say if b equals 2. We figured out b equals 2. So let's go back to f. F is a, x minus 2, natural log of x. There we go. And now we want to make sure that when x is 2, that this has got to be the f value. So 5 equals a, now x is going to be 2. That's confusing, right? Because x is b. And x is 2 and b is 2. X and b and 2 are all the same at this point, at this green messy point that I drew. It's all the same. Okay, now this is just ridiculous. I mean, at this point you're justified in thinking that you did something wrong because nobody would give you a problem this messy, but that is indeed what the problem asks for. So b is equal to 2 and a is equal to 5 over 2 minus 2 natural log of 2. I'm sorry, it really is a mess. But that's how the problem's done. And that is the correct answer to the question. Okay? And you know what? I will I will make the last one another video.